Section: Introduction. In this section, we discuss the transformer architecture, which has become the leading design for large language models, LLMs. However, we face challenges due to its quadratic complexity in processing sequences, which grows with the square of the sequence length, and the increasing size of the key value, KV, cache in full attention mechanisms. To tackle these issues, various alternative approaches have emerged, particularly linear complexity models that reduce the KV cache to a fixed vector or matrix, achieving linear complexity overall. We note that linear complexity models have evolved through 3 generations. The first generation used vector-level hidden states from traditional recurrent neural networks, RNNs. The second generation improved this by using outer products to create 2-dimensional hidden states. The third generation introduced delta rule state transitions, enhancing the models further. Each generation has generally shown better performance in reasoning and retrieval tasks. However, we recognize that the fixed hidden state that allows for linear complexity also limits recall capabilities, leading to poorer performance in this area. To address this limitation, hybrid linear attention models have been developed, combining full attention layers with linear attention layers. While these hybrid models still have quadratic complexity due to full attention, they significantly improve recall performance and have scaled to 400 billion parameters while maintaining competitive reasoning abilities. We observe that while the choice of full attention is usually consistent, the selection of linear attention components seems arbitrary. Most research focuses on the ratio of full to linear attention layers rather than the specific designs of the linear models themselves, often assuming that a better standalone linear model will automatically enhance hybrid performance. We question whether this assumption holds true. Additionally, we find that the optimal ratio in hybrid models is often determined by minimizing loss values, which may not accurately reflect recall performance. Previous work has shown that simply increasing the size of linear attention models leads to diminishing returns. Therefore, we hypothesize that improvements in performance may depend more on how well a model manages and retrieves information from its memory, which we explore through our evaluations. In our research, we conduct a thorough investigation of various linear attention architectures across all 3 generations, analyzing their performance in language modeling and recall when used in hybrid models. We also benchmark pure linear attention models and examine how changing the ratio of full to linear attention layers affects performance. Our study aims to answer 3 key questions. 1. Does a linear attention model with better standalone performance lead to a superior hybrid model? 2. What aspects are more influenced by the ratio of full to linear attention layers, overall language modeling performance or recall capabilities? 3. Which architectural components within linear attention models are most important for optimizing both language modeling and recall? Our paper makes 3 main contributions. We provide a comparative analysis of various linear attention architectures, evaluate the relationship between standalone performance and hybrid model performance, and analyze how the ratio of attention layers affects language modeling and recall, identifying key architectural components that are crucial for these metrics. In the related work section, we review early attempts to reduce the quadratic cost of softmax attention, which led to linear attention models. We also discuss advancements in recurrent networks and hybrid architectures that combine full and linear attention layers to improve recall while managing memory costs. We highlight various models and their configurations, noting that the presence of a few full attention blocks significantly enhances long context quality, primarily influencing recall rather than language modeling loss. Section Summary. In this section, we discuss the limitations of the transformer architecture in large language models due to its quadratic complexity and the growing key value cache, highlighting the emergence of linear complexity models that compress this cache into static hidden states. We explore the evolution of these models through 3 generations, the development of hybrid linear attention models that combine full and linear attention layers for improved recall, and our investigation into the relationship between standalone performance and hybrid model effectiveness, as well as the impact of the full to linear attention layer ratio on language modeling and recall capabilities. Section: Principled Hybrid Architecture Design. In this section, we explore principled hybrid architecture design. While previous studies show that hybrid approaches work, we aim for more systematic design methods. The STAR framework provides a unified mathematical basis for linear attention mechanisms, allowing us to automate architecture creation using evolutionary optimization. Additionally, Poley and colleagues suggest using synthetic tasks to pinpoint specific capabilities and understand how components interact, revealing that the best architectures utilize specialized layers through hybrid structures. These frameworks indicate that hybrid design can progress from mere empirical exploration to more informed optimization of component interactions. Next, we discuss linear attention and its variations. We outline 3 generations of linear time attention mechanisms that inspire our research and explain why we focus on specific models: HGRN from the first generation and HGRN2, GLA, and RetNet from the second generation. For each generation, we summarize the main update rule, highlight what sets it apart from earlier models, and discuss its implications for hybrid design. In the first generation, we have gated vector recurrence. Early linear models simplified the per-token key value cache into a single vector that is updated additively and controlled by a learned gate. This allows for selective memory retention without the issues of vanishing gradients seen in traditional RNNs, but the single-state vector still struggles to hold multiple memories. The second generation introduces an outer product state with decay. To enhance capacity, these architectures use a matrix for the hidden state, accumulating rank 1 outer products while applying a decay gate. The decay mechanism varies among 3 models: HGRN2, which ties the gate across keys and values for a hierarchical memory structure; GLA, which allows for fully data-dependent gates for maximum flexibility; and RetNet, which uses a fixed decay factor shared across positions for simplicity and speed. In the third generation, we see delta rule-controlled forgetting. This approach moves away from per-channel decay and instead uses a dense transition that erases content aligned with the current key before writing new information. This method allows information to flow across dimensions, improving long-range memory recall. The update process resembles a fast, continually trained associative memory, explaining why models like DeltaNet can perform well on tasks requiring recall. We chose these representative models to understand the impact of state size and management in hybrid architectures. Each model serves as a spokesperson for its family of closely related variants. HGRN represents the first generation as a strong baseline for comparison. RetNet stands for fixed decay models, while GLA exemplifies data-dependent gates. HGRN2 represents tied gate architectures, allowing us to study the interaction of different gating strategies with full attention layers in a hybrid model. We briefly survey Generation 3 Delta Rule networks, as they are currently the only public implementations in their category, keeping our main focus on the trade-offs between gating and state size in the first 2 generations. Section Summary. In this section, we explore principled design methodologies for hybrid architectures, highlighting the STAR framework for automated architecture synthesis and the use of synthetic tasks to optimize component synergies. We also formalize 3 generations of linear attention mechanisms, detailing their unique properties and implications for hybrid design, while selecting representative models from each generation to analyze state management and size in hybrid stacks. Section: Hybridization Strategy. In this section, we describe our hybridization strategy and the experimental setup we used. We begin by mapping each input sequence to embeddings, followed by a repeating block of 2 different types of layers. 1. Linear attention layer. This layer maintains a fixed size state that gets updated using an outer product. Since this state does not grow with the sequence length, the computational cost is manageable, adding only a small amount of cache during inference. 2. Full attention layer. This layer uses standard softmax attention to refresh interactions between tokens and updates the key value cache. We alternate between these 2 layers in a fixed ratio, repeating the block multiple times. During training, we process the stack like a transformer, but during decoding, only the full attention layers increase the cache size, reducing memory usage. For our benchmarking, we evaluate various hybrid linear attention mechanisms across several language understanding and recall tasks, including ArcChallenge, HelloSwag, and others. We test different linear to full attention ratios and compare them against a standard full transformer model. All models are pre-trained on a large dataset and optimized using the ADAM-W optimizer. Our empirical study unfolds in 3 steps. First, we compare standalone linear attention architectures with their hybrid forms. Next, we vary the linear to full ratio to see its impact on accuracy and recall. Finally, we analyze different architectural features to understand how they affect performance. We find that linear attention architectures that perform well on their own do not necessarily maintain that performance when combined with full attention. For instance, at the 340M parameter scale, gated delta net has the highest standalone accuracy, but when hybridized, HGRN2 outperforms it at a 6:1 ratio. This trend continues at the 1.3B parameter scale, showing that the combination of attention types significantly alters performance. We also explore how the linear to full attention ratio influences language modeling and recall. While language modeling performance remains stable across different ratios, recall performance improves as we increase the proportion of full attention layers. This suggests that hybrid models excel in recall tasks with more full attention layers, while systems focused on language modeling can function well with higher linear ratios. We further investigate how different tasks respond to changes in the hybrid ratio, noting that recall tasks benefit from more full attention, while other tasks show less sensitivity to the ratio. Section Summary. In this section, we describe our hybridization strategy that combines linear and full attention layers in a fixed ratio to optimize performance on language understanding and recall tasks. We evaluate various configurations and find that while standalone performance may not predict hybrid success, increasing the proportion of full attention layers significantly enhances recall capabilities without adversely affecting language modeling efficiency. Section: Architectural Determinants of Hybrid Effectiveness. In this section, we present our findings on the architectural factors that influence the effectiveness of hybrid models. Our experiments show that hybrid performance relies on 3 key architectural features rather than just one. We provide quantitative data in figures and tables, but our analysis is primarily observational, with more detailed experiments planned for the future. We found that selective gating helps prevent the loss of important information. Models like gated delta net and HGRN2, which use a learned gating mechanism, consistently outperform the transformer baseline by 2 to 5 percentage points in recall when hybridized. In contrast, RetNet's fixed decay method fails to maintain long-range information, resulting in very low recall even with full attention layers. Hierarchical recurrence adds valuable context over different timescales. HGRN2 uses a 2-level structure that keeps broader summaries updated slowly while quickly processing detailed information. This hierarchical approach significantly improves recall compared to a simpler model, indicating that having a recurrent structure helps retain information between attention layers. Controlled forgetting helps manage the amount of information stored. Gated delta net uses a specific rule for forgetting, while HGRN2 employs a different method to achieve similar results. Both approaches prevent the excessive accumulation of outdated information, which is a problem in purely additive models, leading to better recall scores. We also observed that the accuracy of language models changes very little with different ratios of attention layers, but recall improves steadily as we add more full attention layers, peaking around a 3:1 ratio. Models that lack gated or delta-style forgetting do not reach the recall levels of the transformer, highlighting the importance of a suitable architecture. For practical applications, we recommend that practitioners choose a gated, hierarchically recurrent model like HGRN2 or gated delta net, dedicating about 1/4 of the layers to full attention. In our tests with a 1.3 billion parameter model, this setup achieved recall close to that of the transformer while reducing memory usage significantly. We further explored the balance between performance and efficiency for all hybrid models we examined. We connected the computational requirements of the models to their language modeling performance across various settings. Our analysis shows that the pure HGRN model is much more efficient than others, while the full transformer model offers the highest performance but at a lower efficiency. In summary, our study provides clear guidelines for creating memory-efficient long-context language models. We found that hybrid quality cannot be judged solely by standalone performance. Gated DeltaNet performs best in a linear form, but HGRN2 excels when full attention layers are included. Recall, rather than perplexity, is the key factor in determining the best mix of linear and full attention layers. We recommend using a gated, hierarchical model with one attention layer for every 3 to 6 linear layers to achieve optimal performance while minimizing memory usage.